Hello folks, welcome to the class of quantum mechanics. In this class we would be solving the PYQs from quantum mechanics, and we will try to solve as many questions as we can. So we'll start from 2010 onwards. So let's come to our first question. So it states, derive Bohr's angular momentum quantization condition in Bohr's atomic model from the concept of de Broglie waves. So it is a question from 2010. So these questions have been framed in a way that you would see introduction, solution, as well as the conclusion in the answer in the question, and it's the we have tried to produce an ideal answer by which you can get help how to write an ideal answer in your exam. So please focus in introduction, conclusions, as well as on solutions. So the introduction states, the Bohr's quantum atomic model introduces the concept of quantized angular momentum for electrons orbiting the nucleus. This concept is fundamentally linked to the wave nature of electrons as described by de Broglie. So now here the important part is you need to focus on that the de Broglie, the concept of the de Broglie waves links the wave nature of particles. So here is the keyword that you need to focus on, and that should be mentioned in your introduction. Now moving forward to the solution part. According to the de Broglie, the wavelength of an electron is given by lambda is equals to h upon p, where p being the momentum, h being the Planck's constant, and lambda the wavelength of the particle. Now, for an electron to orbit in a circular orbit of radius r, the circumference in which the particle is orbiting, that should be an integral multiple of the de Broglie wavelength. And why that should be the case? See, if an electron moves in a circular orbit, the circumference it covers is 2 pi r, and the distance it is covering should be an integral multiple of the wavelength lambda. And this diagram clearly states that why that should be the case. Now we will substitute the value of lambda from the concept of de Broglie waves in this equation. So 2 pi r is equals to n into h upon p. Now p is the momentum for a particle, so we'll write 2 pi r is equals to nh upon mv. Now we would rearrange the left hand side and the right hand side of the equation. We get L, that being the angular momentum, is equals to mvr is equals to nh upon 2 pi. So what we get here is finally L is equals to nh upon nh cut, or say nh upon 2 pi. So this is the our final expression for angular momentum of the particle. Now let's read the question again. It is stated that we need to derive the angular momentum condition from the Bohr's model. So this was the Bohr's model we started with, and this is the angular momentum condition. So we have satisfied the demand of the question. Now let's come to the conclusion part. Now the conclusion for this is that the Bohr's quantization of angular momentum, it provides a fundamental insight into the discrete nature of the atomic energy levels, leading to the explanation of atomic spectra. Now this should not get ignored, leading to the explanation of atomic spectra. Okay, sorry. Now this quantization of angular momentum, as we would read further in atomic physics class, that this quantization of electrons or the particles that ultimately leads to the formation of atomic spectra. Or some of us would vaguely remember from our class 11th or 12th that the atomic spectra is formed only because of the quantization of angular momentum property of the electrons according to the Bohr's model. Okay, so this thing should be mentioned in your conclusion. That would definitely provide you some extra marks. And this diagram, that is a must in this question. So these three things you have to remember. See, this portion would be done by everyone. The three key points in this question you need to remember is, number one, the wave nature of particles is important in introduction. Secondly, in solution part, everyone would do this derivation. This diagram is important. That would be the key point. And third one, this, second this, and third the conclusion part, that why this angular momentum quantization, what is the significance of angular momentum quantization, and that is the explanation of atomic spectra. So these 3 points would provide you definitely half or 1 or 1.5 marks extra in exam in comparison to others. Okay, let's move forward to the next question. So it was a question from 2010. Let's go forward. Now this is a question from 2011. It states that calculate the wavelength of de Broglie waves associated with electrons accelerated through a potential difference of 200 volts. So now this question is very fundamental in nature. So we'll start again with the de Broglie waves, because the keyword in this question is again de Broglie waves. So the concept of de Broglie waves states that a particle also behaves as a wave whose wavelength can be calculated when they are accelerated by a known potential. So in this question we slightly tweaked our introduction as per the demand of the question, because the de Broglie waves concept, we know it is linking the particle nature to the wave nature. But here, since the question asks us a numerical value when an electron is accelerated through a potential difference of 200 volts, so we tweaked our introduction in a way that it says that whose wavelength can be calculated when they are accelerated by a known potential difference. So this gives examiner a clear idea that we are aware of what we are going to do in the solution part of this question. And we are also aware of the concept of de Broglie waves. So the solution is simply, we know that the kinetic energy of the electron sorry, kinetic energy of the electron is half mv square, or any particle for that matter. We equate it by E into E, where E is the electron charge and V is the potential difference. Now we'll rearrange it and we'll get V is equals to square root of 2 eV over m. So this is the velocity. Now lambda, we know from the concept of the de Broglie waves that lambda is equals to h over mv. Now we'll replace this velocity v from equation A if I state it. So we'll replace v in de Broglie waves from this expression, lambda is equals to h over m into square root of 2 ev over m. So the final expression which we get is this, lambda is equals to h over under root 2m ev. This is the final expression that we're getting. Okay, now what we simply need to do is put the values of the respective constants h, m, e, and the potential we are given as 200 volts. If the voltage would have been in it would have been electron volts, so we would have changed it into the respective quantities, but here it's fine, so we'll keep it. So lambda, we put the value of h, then 2 me, that is the mass of the electron, then charge of the electron, and finally the potential difference. So the numerical value comes out to be 8.6 into 10 raised to the power minus 12 meters. So this is the wavelength when electron is accelerated through a potential difference of 200 volts. So the conclusion part is the wavelength of de Broglie waves associated with electrons accelerated through 200 volts is approximately this, which highlights the wave nature of electrons at atomic level. Okay, so when electrons are at, yani the particles are at the atomic level, it highlights the wave nature of those particles. So this is again an important conclusion from this particular question point of view. Okay, let's move forward to the next question. Okay, third question again from the same year 2011. Estimate the size of the hydrogen atom and the ground state energy from the uncertainty principle. Now we need to find out the size of an hydrogen atom and its ground state energy from uncertainty principle. Okay, so first of all, let's see the introduction. Now it's important here to mention few things in introduction. The uncertainty principle provides a fundamental limit to the precision with which certain particles of physical properties such as position and momentum can be known simultaneously. This principle can be used to estimate the size of hydrogen atom. So we have clearly stuck to the demand of the question in introduction. You will see in further questions related to uncertainty principle that we have slightly modified uncertainty principle as per the demand of the questions, and as per this question's demand, this introduction is apt. Now we'll move toward the solution part. The Heisenberg uncertainty principle is, as we all know, del x, delta p more than equals to h cut over 2. Then for an electron in a hydrogen atom, delta x will be the size, because the uncertainty cannot be more than the actual parameter. We all know for obvious reasons. So del x will be the size of the atom and del p will be the change in the momentum, which would be equals to the actual value, because it can't be more than that. So r dot p more than equals to h cut over 2. Now we know that p is equals to mv, for momentum is mass into velocity. Then we put it here, mvr equals to h cut, as we have seen from the angular momentum conservation, L is equals to mvr. So p we get is h cut over r. So this needs to be highlighted, p is equals to h cut over r. Now we substitute p in the uncertainty principle. So what we are actually doing here is, we were to find the size of the hydrogen atom and the ground state energy. So what we are doing is, we are trying to find out the size of the hydrogen atom first. So r dot p in uncertainty principle, r we have to find out. We are trying to find p in terms of r, so that we can find r from this equation. So r dot, now in place of p we put h cut over r more than equals to h cut over 2. So r comes out to be h cut over mv. Now h cut is a constant, mass we know, we'll put the value of the mass, and v we already know. So we'll put the values of these constant in this equation. Then for the Bohr's radius, that is the smallest, n is equals to 1 shell of the electron of the atom, will get a naught is equals to the respective value, that is 0.53 Armstrong. 0.53 Armstrong. So this is the size of the hydrogen atom. The electron in the hydrogen atom is at the shell, n is equals to 1. So the size of the hydrogen atom comes out to be 0.53 Armstrong. Sorry. Now let's move forward to find out the ground state energy. Now we know that energy is equals to p square over 2m, and from uncertainty principle again we can change the value of p in terms of r, because we know the size of the hydrogen atom already, that is 0.53 Armstrong, which we would put in the expression and calculate the minimum energy. So we replace p in terms of r, that is h cut over r, and p square gives us h cut square over r square. Then E is equals to h cut square upon 2m multiplied by a naught square. Then a naught is again 0.53 Armstrong. We know the value of a naught. H cut square is a constant. 2m, 2 is a constant. M we know the mass of the electron. So we'll put all the values and we get energy is equals to minus 13.6 electron volt. Okay, so this is the energy of the hydrogen atom, which we have calculated the ground state energy of the hydrogen atom from the uncertainty principle. Here the crux is that we have to find out all these things from uncertainty principle. There are numerous ways you can come up and say that there are multiple ways to find out the same thing, but yes, the demand of the question is we need to find out from the uncertainty principle. So keyword here is uncertainty principle. That is why we have started our introduction from the concept of uncertainty principle and related it somehow to find out the size of the hydrogen atom and the energy of the hydrogen atom. So it's a very fundamental question. So the conclusion simply comes out to be the size of the hydrogen atom is approximately 0.53 Armstrong and the ground state energy is this much. So that's all about this question. No rocket science. Let's move forward. Okay, let's come to the fourth question. Now this is a question from the year 2012. Let's read it. Use the uncertainty principle to estimate the ground state energy of linear harmonic oscillator. Okay, now see, the earlier question was to find out size and energy of hydrogen atom. Now here it is asking linear harmonic oscillator. The system has changed, but the core principle still remains the same. We have to find out the ground state energy using the uncertainty principle. So both the questions are similar, but now I will show you the change in the introduction. Okay, You can have used, someone has used this as an introduction also, but in a similar type of question, if you use introduction like this, which we have used in this particular question, you would definitely gain some extra marks. Let's read it. The uncertainty principle formulated by Werner-Heisenberg states that two conjugate pairs which do not commute in quantum mechanics can never be precisely measured simultaneously. In this case, in this particular case, it states that the energy and time can't be exactly determined simultaneously. So this is very important when it says, because the fundamental concept of Heisenberg uncertainty principle boils down to the conjugate pair. So if we have these conjugate pair which do not commute, so conjugate pair basically mean the pairs which do not commute, so their commutator is not 0. So if they do not commute, then they can never be simultaneously be measured precisely with 100% accuracy. Okay, so we started our introduction of Heisenberg uncertainty principle with this fundamental concept, and we related it with the fact that in this particular question, since we need to find the ground state energy, so in this case it states that energy and time can't be exactly determined. If there would have been the minimum size, find out the size of the linear harmonic oscillator, then we would have written, in this case it states that the momentum and the position can't be exactly determined because they are conjugate pair which do not commute in quantum mechanics and they can't be precisely measured. And it is true for both energy and time, position and momentum, k and x, as we all know. Okay, so this particular introduction, if you write in exam, you definitely gain some extra marks. Okay, so let's move towards the solution point of view. Solution part. For a linear harmonic oscillator, the potential energy is given by Vx is equals to half kx square. This is the basic expression that we all know. The total energy would be kinetic plus potential, p square by 2m plus half kx square. Now using the uncertainty principle, delta x, delta p more than equals to h cut over 2, we set delta p somewhat equals to p and delta x as x. Why is that so? For obvious reasons that we all know, because the uncertainty in an expression can't be more than the expression itself. X dot p more than equals to h cut over 2, and from here we get the expression of p in terms of x. So this would be used in most of the places related to some tweaks in uncertainty principle, that the relation between momentum and the position. So you just note it down in your mind that whenever there is a question related to some changes in the uncertainty principle, you have to find out momentum in terms of x or x in terms of momentum. The things will go on forward from there only in 80% of the cases. Now we substitute this into the expression. Energy is more than equals to p square by 2m. So we replace p square by h cut upon 2x. So h cut upon 2x ka whole square over 2m plus half kx square, as the expression is. Now minimizing e with respect to x. Okay, so we simplified, first of all we simplified it. Now we'll minimize it. How to minimize an expression? Delta e over delta x is equals to 0. Okay, now delta e dE over dx is equals to 0. Now you will find out the value of x from here, as we get x square is equals to h cut upon 2 square root mk. Now you will put this value of x square in this expression to get the value of energy. So we put the value of x square in this expression, we get energy is equals to h cut omega by 2. Is that clear? Then omega, where omega is square root of k by m. Okay, now the story doesn't end here. Okay, now you can do this and the question ends as we have ended in this solution as well. But if you could add one more thing here, that dE over dx is equals to 0 for minimizing the energy, and at the same place if you can write that double derivative of this energy d2e over dx2 for the minimum thing is positive, that is more than 0, then definitely you will get some extra marks, 0.5 marks extra, because examiner now knows that you have a very clear concept that while doing dE over dx we have two cases. It could have been a minima or it could have been a maxima, but when you do the double derivative and the double derivative comes out to be positive, then definitely the value is a minima. This concept should be there in your mind, and if examiner knows this, you will definitely gain some extra marks in this question. So we have not written this here. This is for those who are watching this lecture very sincerely. We are giving you some extra added values from this lecture, and you can clearly see that the double derivative would be positive if the energy here is minimum, okay, which comes out to be h cut omega by 2. So you have to mention this, okay. So the key point in this solution is double derivative of energy would be positive. You have to highlight this point. Now the conclusion comes out to be very simple, that the ground state energy of linear harmonic oscillator is h cut omega by 2, demonstrating the 0 point energy due to quantum fluctuations. Because of the 0 point energy, the position and momentum of the oscillator in the ground state are not fixed but have a small range of variance in accordance with the Heisenberg uncertainty principle. Okay, so simply this the conclusion is trying to say that because of Heisenberg uncertainty principle, we arise with the concept of 0 point energy, okay, which is not the case in classical mechanics. We have no such concept as 0 point energy in classical mechanics. Why? Because of the application of uncertainty principle in quantum world. Okay, so just write these two lines and your conclusion and this entire question is done and dusted. Okay, so let's move forward. So this is a question from the year 2013. Okay, it states that in a series of experiments on the determination of the mass of certain elementary particle, the results showed a variation of plus minus, you can see here it is plus minus 20 ME, plus minus 20 ME, where ME is the electron mass. Estimate the lifetime of the particle. Now we need to estimate the lifetime of the particle. So again, you see here plus minus 20 ME is given the variation. We need to find out the lifetime. So from this variation in the mass and estimating the lifetime of the particle, suddenly a thought in your mind should strike that we have to apply. What we have to apply? Just think for 5 seconds in your mind. So we have to apply here uncertainty principle again. So this is a question again from Heisenberg uncertainty principle. Now, as in the last question, we had this introduction. Again, the question is from the basic concept of the Heisenberg uncertainty principle. It involves no other concept other than HUP. So we'll use exactly the same introduction. Okay. So this is called the smartly writing an answer. You have certain topics like Heisenberg uncertainty principle. You have the concept like de Broglie waves concept till now. So we have a set introduction and a set conclusion for both the major topics, which we will use. We will change a bit as per the demand of the question, but more or less the introduction and conclusion for both the broader topics would remain exactly the same. The introduction is the uncertainty principle formulated by Werner Heisenberg states that two conjugate pairs which do not commute in quantum mechanics can never be precisely measured simultaneously. In this case, it states that the energy and time can't be exactly determined simultaneously. Okay, so again, since it was a question related to lifetime of the particle, then the energy and time can't be determined simultaneously. Okay, same concept, the conjugate pair concept. Examiner would be definitely impressed if you write this, okay, and you gain these marks. Let's come to the solution part. Now, given the mass uncertainty, delta M is equals to plus minus 20 ME, where ME is the electron mass, we use energy time uncertainty. Delta E delta T more than equals to h cut over 2, basic expression of the uncertainty principle. Now energy is E mc square, E is equals to mc square, delta E becomes delta M into c square. And now just a very basic question, why not delta E is equals to delta M into delta c square? Just answer it in your mind, okay? Why not? Why not this? Why only delta E is equals to delta M into c square? Why not this? Very fundamental question. Substitute. So we'll substitute the value of delta M from the question. Now see, here is a variation of plus minus 20 ME. So what is the total change in mass? So the total change in the value of mass is 40. So we'll write 40 me into c square. Okay, so using the uncertainty principle, 40 me c square, that is the energy, into T, that is delta E, it is delta T more than equals to h cut by 2. Okay, so from here we get delta T as h cut over 2 into 40 me c square. Now this is the expression. H cut is a constant, me we know very well, 9.1 into 10 raised to the power minus 31 kgs, and c square is again a constant. So from here you get delta T is 1.61 into 10 raised to the power minus 23 seconds. Okay, so this is our final answer. So the key point till now is, number one, the conjugate pair thing, that is the introduction. Number two, the total change in mass is 40, not 20, because it is plus minus 20 me. This you have to note. And let's come to the conclusion. The estimated lifetime of the particle based on its mass uncertainty is 1.61 into 10 raised to the power minus 23 seconds. It decays via a weak force into a nucleon and a pion, which highlights the precision required in high energy physics experiments and the stability of lambda particle. So now this is important. The question stated that there is a particle which had a variation in mass plus minus 20 me, estimate its lifetime. We got a certain lifetime as this. Now the conclusion is saying that this particular particle would decay into nucleon and a pion, and which is of fundamental importance in high energy experiments and the stability of lambda particle. Alright, I hope this conclusion is very clear to all of you, because it also has relation from molecular as well as the atomic physics. If right now you are not able to understand how is it relating to the stability of lambda particle, then watch our lectures of atomic and molecular physics PYQs. We'll explain this concept there. Okay, so the stability of lambda particle. For now, you can just remember this particular conclusion. Okay, let's move to the next question. It is a question from 2014. Find the de Broglie wavelength of neutron and electron with the kinetic energy 500 electron volt. So again, the core concept here is de Broglie wave. So we'll use a somewhat similar kind of introduction as we used in our question 1 and 2. So the introduction here is, the de Broglie wavelength is a very fundamental concept in quantum mechanics introduced by Louis de Broglie. It describes the wave-like behavior of particles and is inversely proportional to their momentum. Okay, describe the wave-like behavior of particles and is inversely proportional to the momentum. Now, why we wrote inversely proportional to momentum here? Now we are clearly seeing that the question is related to the kinetic energy. Here we will have to change momentum in terms of kinetic energy. So we mentioned it in the introduction itself that the de Broglie wave is inversely proportional to the momentum, so that examiner now knows that what we are going to use in our solution. Okay, so the solution is, for a particle, the de Broglie wave is this, lambda is equals to h over p. Now this concept we have to use, this formula we have to use first for neutron and then for electron. So energy is p square over 2m. P comes out to be, we know, under root 2 me. So we'll calculate momentum. Energy we know is 5 electron volt, and m we know the mass. So what changes? See, just see this. P is equals to under root 2 m e k. So e k is, we know, is 500 electron volt. Pardon me. Now mass can be of one time, it can be for neutron, and other it can be for electron. So mass of electrons are different, it is me, and mass of neutron is different than mass of electron, mn. Okay, so what changes in the entire expression or in the entire calculation is just the mass of electron and mass of neutron. Otherwise they both are subjected to the same energy, that is 500 electron volt. Okay, so just calculate the momentum. 2 me for neutron, it would be 2 mn ek. So mass of neutron you would put here and then ek. Okay, so momentum comes out to be this much, and put the value of momentum in the de Broglie waves formula, lambda is equals to h upon p. So you get lambda is equals to this much for a neutron. Okay. Okay. Let me give you a task. We have neutron and proton. Okay. Let's not calculate it. Let's consider that there would have been an MCQ, and you would have been asked that which one of them would have the more wavelength, more lambda. Would lambda n be more, or lambda proton, this neutron or electron? Which would be more, lambda n or lambda e? So how would you know that which wavelength would be more without calculating or without even using a pen? For that, you just need to remember that there is an inverse relationship between lambda and mass. Okay, if mass is more, lambda is less, and if lambda is more, then mass is less. Okay, so just remember this relationship. You would get the answer without calculating that which of them is correct. Okay, so you can verify your answer also by this. Calculate the wavelength for both the particles, neutron and electron, and then finally see that whether this concept applies to your numerical values or not. Okay, fair enough. Let's move forward. The electron with kinetic energy of 500 electron volt, then we just replace here the mass of electron. Other things remain the same. Okay, so we calculate and we get lambda for electron as this for electron 5.48 into 10 raised to the power minus 11. So we get lambda for neutron as 1.28 into 10 raised to the power minus 12, and for electron as 5.48 10 raised to the power minus 11. Okay, so which one of them is more? Which one of them is more? This one is more, minus 10 raised to the power minus 11 is more. That means electrons lambda is more. Electrons lambda is more. Okay, so that means electrons mass is less, and we know that yes, mass of electron is less than mass of neutron. So we can clearly see this relationship. That means our answer is probably correct. At least the order of the answer is, comparative order of the answer is correct. Okay, this is a very general confirmation of our answer. All right, let's move to the next question. This is a question from 2014. The mean life of lambda particle is 2.6 into 10 raised to the power minus 10 seconds. What will be the uncertainty in the determination of its mass in electron volt? Now, this is important, that in electron volt we need to find out. Again, you see, the question is the mean lifetime and the uncertainty principle. So yani it is talking about delta E delta T thing. Okay, again the same fundamental concept of HUP, Heisenberg uncertainty principle. Okay, so we'll use the same introduction as we used earlier. The uncertainty principle formulated by this which two conjugate pair which do not commute in quantum mechanics can never be precisely measured simultaneously. In this case, it states that energy and time can't be exactly determined simultaneously. Fair enough. So fair enough, delta E delta T more than equals to h cut over 2. Then delta E we know is delta m into c square. Delta T more than equals to h cut by 2. Then delta m more than equals to h cut over 2 c square into delta T. Given delta T is 2.6 into 10 raised to the power minus 10 seconds. H cut is this much and c is this much. We all know this. Just put the values. Here h cut is a constant, delta T we are given, c square we know. We find delta m, that comes out to be delta E we found out, that is 0.202 into 10 raised to the power minus 24 joules. Okay, so we got the answer in joule. Now we need to find out in electron volt. So what we'll do, we'll simply divide this expression by 1.6 into 10 raised to the power minus 19. So we'll get this expression finally, 1.26 into 10 raised to the power minus 6 electron volt. So this is our final answer. So the key point in the question is this introduction. If you write this introduction, you definitely gain 0.5 marks. Okay, and this calculation we can't add much into this. Okay, you can simply do one more thing, that you can write now in conclusion the significance of the lambda particle, or what is a lambda particle, or what is the physical significance of a lambda particle in nuclear physics or in particle physics or in high energy physics. You can formulate the things around that. Okay, so a particle with this energy can decay into a via a weak force into a nucleon and a pion, which highlights the precision required in the high energy physics and the stability of the lambda particle. I hope the conclusion is clear. It is exactly the same as in the previous question, because the question's demand is same. Question's demand is same, meaning by to say that the concept used in the question is delta E delta T more than equals to h cut over 2, and it is a fundamental subatomic particle in which delta T is given and we need to find out delta E. Okay, let's move forward. Okay, so this is a question from 2016, and it's a very basic question again. Let's read it. Find the energy, momentum and wavelength of photon emitted by a hydrogen atom making a direct transition from an excited state with n is equals to 10 to the ground state. So what we need to find out? Just note it down. We need to find out energy, we need to find out momentum, we need to find out the wavelength of the photon emitted from n is equals to 10. These all three things in condition from n is equals to 10 to n is equals to 1. Also find out the recoil speed by the of hydrogen atom in the process, and we need to find out the recoil speed. So we need to find out 1, 2, 3 and 4 numerical values. Okay, so let's move forward. Now introduction. So first we need to identify that what is the fundamental concept that is being highlighted here, and here the concept is the transition of electron from one state to another. It changes, it radiates some energy, it has some momentum associated with it, and there is definitely some sort of wavelength associated with the particle. So we need to find these three things out. Okay, so our introduction would revolve around the concept of transition of electron in a hydrogen atom. Okay, that will meet the demand of the question. So whenever an electron makes a transition from higher energy levels to the lower energy levels, it radiates energy in form of a quanta. This transited photon had a momentum and corresponding wavelength associated with it. Okay, so we just simply mentioned here a thing that whenever there is a transition from a higher, because in this question the electron is being transmitted from n is equals to 10 to n is equals to 1. So there is a transition from a higher energy level to a lower energy level. So our introduction basically hits the demand of the question and states that whenever there is a transition from higher energy level to a lower energy level, there is a radiation. The energy is radiated in form of quanta. The transited photon I'm sorry, the transited photon has a momentum and a corresponding wavelength associated with it. So now examiner knows that we know the fundamental basic concept behind the question asked. Okay, now the solution part, the radiation is taking place, the transition is taking place from n is equals to 10 to n is equals to 1. The energy, as we know, for a hydrogen atom is minus 13.6 electron volt over n square. Okay, it is for the transition from nth level, energy at the nth level. The energy of the photon transmitted would be delta E, that is the final. See, always what is the energy of the photon transmitted? Energy of the delta E of the photon transmitted, the final energy level minus initial energy level. Okay, because we need to take care about the sign of the energy as well. So final minus initial. So here the final energy level is energy level 1 minus energy level 10. So E1 minus E10. So E1 minus E10. E1 we know is minus 13.6 and E10 we know is minus 13.6 over 10 square. Okay, so we solve it, E1 minus E10, we put the value and we get delta E as 13.464 electron volt, and that is positive. Okay, now you will tell us in the comments that what is the significance of this delta E is equals to positive sign here. why is this positive sign coming and what is the significance of this positive sign. Okay, you have to be proactive and you would be answered in the comment section only. The wavelength lambda of the emitted photon E is equals to hc by lambda. Lambda here we can rearrange our left hand and right hand side as hc over E. Lambda is equals to hc over delta E. Okay, fair enough. Now just put the value of h, c and delta E as we have calculated here itself. So lambda comes out to be 91.3 nanometers. Okay, so let's go back to the question again. We were asked energy, we have found it out, momentum and wavelength. Energy we have got, wavelength we have got. So energy, wavelength we are done. Let's come to the momentum. Now momentum is, we know, P is equals to E by C. So energy we already know, 13.6 into 13.464 into 10 raised to the power nothing, because it is in electron volt. So to convert it in joules, we'll have to multiply it by 1.6 into 10 raised to the power minus 19 upon C. C is 3 into 10 raised to the power 8, and we get this particular expression. So simply the momentum comes out to be 7.19 into 10 raised to the power minus 27 kg meter per second, and the unit is very important. Okay, you cannot miss unit in numerical questions. You would lose your marks for no good reasons. It is the worst way of losing marks, by not putting units in your numerical answers. Okay, at least put units in your final expression, whatever you are asked. We are asked momentum, so we'll put the particular unit. We are asked wavelength, we will put the unit. We are asked energy, then we will put the particular SI unit of that expression. Okay, now the fourth part was to find out the recoil speed of the hydrogen atom. So how can we calculate the recoil velocity? Whenever the term recoil velocity comes out, we suddenly remember of the concept of momentum, because whenever there is a recoil, there is a conservation of linear momentum. So using the conservation of linear momentum, the momentum earlier would be equals to momentum after collision. So P is equals to capital M VR, that is the recoil velocity. So VR would be P by M. Now M is the now M is 1.6 into 10 raised to the power minus 27 kg. Okay, this is our mass, and the momentum we have already found, 7.19 into 10 raised to the power minus 27 kg meter per second. Okay, so this is our momentum and this is our mass. So we get the velocity as 4.3 into 4.3 meter per second. Okay, this will be our final expression. Again, the units here are important, the recoil velocity. All right, so this was a question from 2016. All right, now the conclusion is, the photon emitted in the hydrogen atom transition has a wavelength of 91.3 nanometer, and the recoil speed of the hydrogen atom is approximately 4.3 meter per second. These results illustrate the principles of energy, quantization and conservation in atomic transitions, with applications in spectroscopy and quantum mechanics. Okay, so in spectroscopy and quantum mechanics, there are some applications in spectroscopy and quantum mechanics. You have to write this. Okay, if you write this term, that applications, the application part, the physical significance part in your conclusion, then you definitely gain some extra marks. So the particular concept of quantization of energy and in atomic transition has applications in spectroscopy, as we will read in our atomic and molecular physics course. Okay, spectroscopy and quantum mechanics. So we are done with this question. If there are some numerical or calculation errors, then you can please point them out. Okay, from our end we have checked it multiple times, but still there can be some issues, so please point them out. Okay, so this is a question from 2016. An electron is confined to move between two rigid walls separated by 10 raised to the power minus 9 meters. Compute the de Broglie wavelengths representing the first three allowed energy states of the electron and the corresponding energies. Okay, so here the concept is again the de Broglie wavelength. Okay, first three allowed energy states of the electron and the corresponding energies we need to find out. The de Broglie wavelength is a fundamental concept in quantum mechanics which describes the wave nature of the particle. According to the de Broglie hypothesis, every moving particle has a wave associated with it and it is inversely proportional to the momentum. Okay, so this is our basic introduction that we are using everywhere in de Broglie wave concept. Number one thing we are using that the wave particle is related to wave, and number two we are using that wavelength is inversely proportional to the momentum. So these 2 points are there for de Broglie wave concept questions. So now question solution part is, we know that the energy levels, it is a infinite well n square h square upon 8 ml square, where n is the principal quantum number that starts from 1 2 3 and so on and so forth. H is the Planck's constant having the value of 6.626 into 10 raised to the power minus 34 joule seconds. Mass of the electron being again 9.1 into 10 raised to the power minus 31 kg. Now let's put the value. Now first energy level E1, n is equals to 1, fair enough. H is a constant, 8 ml square, that goes again a constant. So this part is a constant for all energy levels. What changes is this. Okay, so E1 and then we'll get E2 and then we'll get E3. So it would be 1 square, then here it would be 2 square, and here it would be 3 square. Here the regions would be constant, only these values would change. So 1, 4 and 9. So these multiplication factors would change and rest of the things would remain the same. So for n is equals to 1, the expression is 6.03, 10 raised to the power minus 20 joules. For n is equals to 2, we have 2.41 into 10 raised to the power minus 19 joule. For n is equals to 3, we have 5.43 into 10 raised to the power minus 19 joules. Okay, so for these three allowed energy states, we have the corresponding energies. Now, what else does this question ask? It asks allowed energy states and the corresponding energies. Compute the de Broglie wavelength representing the first three allowed energy states and the corresponding energies. So we have found corresponding energies. Now let us find de Broglie wavelength from these energies. So we know lambda n is equals to h over pn. Pn we know is under root 2 me. So for lambda 1 will be h upon my p1. So what would be p1? P1 would be under root 2m e1, simple. So we already have e1 as this expression, this particular expression e1 we have found 6.03 10 raised to the power minus 20. So we'll put 6.03 10 raised to the power minus 20 and m into 2 will get p1. So p1 comes out to be this thing, and then p1 will put in de Broglie wave concept, lambda 1 would be h upon p1, then lambda 1 would be h upon p1. This is p1. Okay, so we get lambda 1 as 2.007 into 10 raised to the power minus 9 meters. Same goes for n is equals to 2 under root 2 m e2. This is e2, then p2 we get this, and then we'll put the value of p2 in lambda 2 barabar h is equals to h by p2. So we'll put the p2 here, and lambda 2 will get 10 raised to the power minus 9 meters. Fair enough. Same for n is equals to 3, 2m, this thing is e3, we'll get p3, then p3 we got, then lambda 3 is equals to h upon p3. We'll put the p3 here. Lambda 3 is 6.6. It comes out to be 6.6 into 10 raised to the power minus 10 meters. Okay, now if a student does only this much, okay, reads the question, writes introduction, writes conclusion very well, and leaves it here and writes a conclusion as well, but you might get 1 marks extra if you plot the energy levels in this particular question, because there is a scope of a diagram, and wherever there is a scope of a particular diagram in a question, you must make it. You must not lose opportunity of gaining a half mark or 1 mark in every question extra. Wherever there is a possibility and it is relevant, please draw a particular diagram. So here we can plot energy levels and the wave function and the corresponding wave functions. Okay, so we have shown here the blue one is wave function psi1. So this is a psi1 graph. Okay, let me not use the pen. It is psi1. Just a sec, sorry. Okay, so this is psi1, this line is psi1. Okay, this is psi1, and then red one is psi2, this is psi2, the second state, and the third state is psi3. This is the plot for psi3. Okay, so it is psi n versus x by L graph. Okay, so this is very very important. If you make it, you definitely gain 1 marks extra. Okay, this will attract the examiner. Now for energy levels, this was for the wave functions and this was for the wave functions. Now for the energy levels, energy level C, E1 is here and then E9 is here, E1, E4, E9. So it is basically first energy level, and then it is basically E1 means first energy level. Now E4 is the second energy level because E2 it is, but the square term n square makes it 4, so we have denoted it as E4. It is not the fourth level, it is the second level. Okay, and now this is the third level. Okay, this diagram. Now in this diagram, what else is hidden that an examiner would provide you even half mark extra if you draw this particular diagram properly? Just think about it. See, the gap between the energy levels is very very important. Okay, the energy gap between the first and second and the ground state from the first and the second level is lesser than the energy difference between the second and the third level. You can clearly see that this gap is less than this gap. So you have to make the diagram in a way that it is clearly it is clearly depictable to the examiner that you are aware of the fact that the energy gap between the first energy level and the second energy level is less than the energy level difference between the second energy level and the third energy level. Okay, because 9 minus 4 comes out to be 5, and here 4 minus 1 comes out to be 3. So clearly this space is more than this space. So this diagram is very important and you have to make this diagram very properly. Okay, this is the value addition diagram for you. Now let's move to the conclusion part. These values reflect the quantized nature of energy levels in a confined system, significant in the fields like quantum computing and semiconductor physics. So it is used in quantum computing, the concept of this energy level quantization, and it is as well as used in semiconductor physics. You have to remember it and note it down in your notes, or you can simply use this PDF as notes as well. But this fact that it is used in quantum computing and semiconductor physics in conclusion would definitely attract the examiner. Let's move to the 10th question. It is again from the same year 2016. Okay. So the question states a typical atomic radius is about 5 into 10 raised to the power minus 15 meters, and the energy of beta particle emitted from a nucleus is at most of the order of 1 mega electron volt. Prove on the basis of uncertainty principle that the electrons are not present in the nuclei. Okay, so here the question asks us that we have to prove why electrons are not present inside the nuclei. Okay, again we have to use the uncertainty principle. So the uncertainty principle which we want to use is, again we'll use the same sort of introduction that we used earlier. We'll start the introduction from the conjugate pair concept, which would state that the conjugate pair which do not commute in quantum mechanics, that can never be precisely measured simultaneously. In this case, okay, so here is I think a typo from our side, I'm very sorry for it. So it should be, in this case it states that position and momentum, not energy and time. Okay, I think there is a typo from our team. So position, and in this case it states that position and momentum can't be exactly determined simultaneously. Okay, so again the same question, just a little bit of tweaking, and we framed the new introduction for a new question. All right. Okay, now the solution part. Delta x, delta p, we know h cut over 2. Now, okay, it is momentum, it is position, we all know this. H cut, value of H cut, they have found out. Okay, so I would suggest you one thing, that please remember the values of few constants. For example, H cut, that is h upon 2 pi. This would be used so frequently in numericals that you can't every time calculate it. Okay, so just remember h upon 2 pi is 1.055 into 10 raised to the power minus 34 joule seconds. Okay, so we'll try to give you one pager also, in which we would write the such sort of numerical values which are relevant or which are of most importance in exam, and they are frequently repeated in numericals as well. So we'll try to jot them down in a paper, for example this particular thing or various other things that keep on coming in numericals. We'll try to make a formula sheet in which we'll note down these things for you. Okay, so h cut, the value of h cut is 1.055 into 10 raised to the power minus 34 joule seconds. For an electron confined within the nucleus of radius, we know that the radius of the nucleus is 1 Fermi of the order of 10 raised to the power minus 15 meters. You can very well ignore this 5 term also. Okay, it's not a very big deal if you ignore 5 into 10 raised to the power minus 15 meters. You can simply write 10 raised to the power minus 15 meter as well. So the numerical value would change in your answer, but the order of the answer more or less remains the same. Pardon me. The uncertainty in the position delta x is approximately the size of the nucleus. Alright, we know because the uncertainty cannot be more than the size of nucleus. Either it has to be less than or has to be equals to the size of the nucleus. Now we'll substitute, as I said you, that this concept of replacing momentum in terms of x or replacing x in terms of momentum is very frequently used. So delta p more than equals to h cut over 2 delta x. Substituting the values, delta p is more than equals to 1.055 into 10 raised to the power minus 34. As we saw here, we found out the value of h cut, and then upon 2 delta x, here is 2 delta x is again the radius, the nucleus inside 10 raised to the power minus 15 order, and we calculated it and we get 1.055 into 10 raised to the power minus 20 kg meter per second. Okay, so momentum, unit of momentum is kg meter per second. How it comes? I hope we all know this. Momentum is mass into velocity, kg meter per second. Okay, now kinetic energy is E is equals to p square over 2m. So we know the value of p now. Just put the value of p here, p square over 2m. The value of m we are aware of, 9.109 into 10 raised to the power minus 13 minus 31, beg your pardon, delta, then E is this much, and E comes out to be 6.1 into 10 raised to the power minus 11 joules. So this is the energy in terms of joule. If I need to find out in terms of electron volt, then just divide it by 1.6 into 10 raised to the power minus 19. We get 3.81 into 10 raised to the power 8 electron volt, or we shift the two decimal places, 381 into 10 raised to the power 6 electron volt. This is mega electron volt. So 381 mega electron volt. Okay, so it comes out to be 381 mega electron volt. Now the conclusion part. So this is the answer. Okay, now this is not the answer. This is just the energy that an electron would require to remain inside a nucleus. Okay, the question was that prove that electron cannot reside inside a nucleus. Now we have come up with the answer with a numerical value of the energy of electron. What if an electron independently resides inside a nucleus? Then the energy would be 381 mega electron volt. Alright, this is not completed right now. Now we'll complete it in our conclusion. The minimum energy of electron confined within the nucleus according to the uncertainty principle is approximately 381 mega electron volt. This is significantly higher than the typical energy of the beta particle emitted from a nucleus, which is about 1 mega electron volt. So whenever there is a beta particle emission and we experimentally try to find out the energy of the electron emitted during a beta emission, then we see that the energy associated with that particular particle is 1 electron volt. Therefore, the electrons cannot be present in the nucleus, as their confinement would require them to possess unreasonably high energy, that is inconsistent with the observed, or you can also say experimental, nuclear phenomena. I hope you are getting the point. The mathematical value of electron to reside inside a nucleus comes out to be 381 mega electron volt, but during a beta particle emission, we see that the particle that is emitted from inside a nucleus, the energy is 1 mega electron volt. So this proves that electrons cannot reside inside the nucleus, because to possess inside a nucleus they need very unrealistically high energy, 381 mega electron volt, but the actual energy of the particle coming out of the nucleus is only 1 mega electron volt. So it is not possible for electron to reside inside the nucleus, because it violates, or in simple words if I say, it violates the law of conservation of energy, because it requires more energy than that actually is. Okay, so this ends up with this particular question, and you have to write this answer here, this conclusion here. Why 380? You cannot leave simply after calculating energy as 381 mega electron volt. You have to show this, that why 381 mega electron volt is not possible. Okay, beta particle emission experimentally reveals 1 mega electron volt to be the energy of the particle emitted out of nucleus. Okay, so it was the last question in this lecture. These are the total 10 questions that we have. So we have solved all the 10 questions from 2010 to 2016, and in the next lecture we'll continue from 2000, the remaining questions of 2010 till 2000. We'll try to solve from 2016 onwards. See, we completed this question number 1, question number 2, 3, 4, 5, 6, 8, 9 and 10th. We have completed till 2016. So we have completed from 2010 to 2016. In next lecture we'll try to complete 2017, 19 and 17, 18, 19 and 20. Okay, we'll try to complete them. So we are moving topic wise. Okay, this from 2010 to 2016 we have covered the basic concepts, questions from Heisenberg uncertainty principle, questions from de Broglie wavelength, and other fundamental questions that relate to the peripheral topics from these particular topics. So from these topics from 2010 to 2016 the questions have been completed, and we are moving forward in a similar way as we have designed our simulators. That is a repository of the PYQ questions that our team has made, which is topic wise arranged, and not a single question from 2010 till 2022 I think has not been missed. So you can refer to that also. We are moving according to our simulator set PYQs. Okay, I hope you liked the lecture. Thank you very much.